All right. So thank you for coming, everybody. We're going to start going over the SN4 electrical system. Um, so let's just jump right into it. I always like to say why we're learning about things at the beginning because I feel like it helps put everything into perspective. Like, there's no point in learning something if you can't use it. Like, some things are just fun to know, but you should learn things to be able to apply it. So today we're going to be learning what circuits actually exist on the car and what do each of them do. There's a lot of things that are going on the car at any given moment, so there's a lot of information here. Um, when is the car dangerous to interact with? This is a high voltage system, so there will be points of operation where you will likely not want to be near the car, not want to touch the car, and just be very safe working around it. So that's also some important information here and what computation occurs on each board. So sort of what software is running on each one, what is it making sure is going correctly, what safety stuff is it checking? Pretty much everything has safety protection in some sort. Um, so I sent this out previously in Slack, so if you want to follow along in the education channel, you can go to the SN4 EECS diagram and just zoom in when I'm talking about stuff. If you're more of a visual learner, I feel like that might help. But at a very high level, you can see there's a lot going on here. You probably can't read anything from where you're sitting, but this is what we're going to go through tonight. So I'm just going to start because there's a lot to get through. For the first half, we're going to start with going through the low voltage sections. And this presentation will slightly be following the flow of how things work if you were turning on the car to start driving it. So it's sort of like I walk up to the car, how do things start working in what order? So the first system we're going to talk about is the LVPDB, which is in this section of the low voltage system. And so this is the low voltage power distribution board. And so we start turning on the car by turning the grounded low voltage master switch, which connects the low voltage battery to the LVPDB. And that has to be on the right side of the car around driver's shoulder height. That's in the rules. So that's where it is if you're looking for it on the car. And this board spreads power across the entire car through all the different nodes and through our CAN and power bundle, which daisy chains every single CAN communication node together. So we basically have a wire connecting from board to board, and every board has two ports. So it goes in and then back out and on to the next one. The low voltage power distribution board, it distributes power to beyond just the low voltage PCBs that are running on the car. We also have to take care of radiator fans, coolant pump, accumulator fans, the autonomous computer. It also toggles a switch for the brake light just because it's mounted near the brake light, so it's easiest to put it on there. And it's also the source of power for the shutdown circuit. The shutdown circuit is extremely important for the car, and we'll be going over that Thursday at GM because this Thursday is actually the high voltage safety talk at GM. So part of that includes going through the shutdown circuit and all the components. And it also powers the low voltage power for the motor inverter, which we'll talk about at the end of this. And besides just sending power to each of these, it's also logging the voltage and the current on each of these connections. And the reason we want that kind of data is it allows us to figure out our low voltage power requirements so we can rationalize downsizing the low voltage battery. So if we know the power draw of everything on the car and we can make our low voltage battery smaller, it's actually pretty chunky right now. That can help us save weight on the car, and that's always good. We want it to be as small as possible. Are there any questions on like low voltage power distribution, what sort of data we're collecting, what it's monitoring for? Yeah, sure. Yes. Yes, I meant to grab some of the PCBs from RFS yesterday, but I forgot. So I meant to be passing them around so you guys can look at them, but I can show you photos afterwards. But each slide that I go through here is going to be a separate PCB. So the LVPDB is one PCB, and the GLV master switch is an actual switch that's on a panel. So those are like two separate components, and the LVPDB contains all of that hardware. Yeah, yeah, it's about yay large. Yeah, I really wish I had remembered to bring those because that was the hands-on portion of today's lecture. Um, and one more thing, besides just monitoring the voltage and current on each of these buses, it will also shut down that branch if the voltage on that bus goes too high or too low, so over voltage and under voltage faults. It'll also shut down the branch if the current goes too high. So over current, like if your system's broken and it's short and it's pulling too much current. Yeah.
Yeah, so the entire like low voltage system is just powered through one 24-volt battery, or is it like several 20?
Yes, it's one 24-volt battery. Right now it's a 20 amp hour lithium iron phosphate battery. Um, and that's what we used last year. And we got some data to tell us that's good, but we still have some big question marks in our low voltage power budget, mainly accumulator cooling and how much current those fans are going to take. So that's what we want to collect data on this year to hopefully get a smaller battery. All right. Uh, so the next board on the car that we're going to talk about is the APPS and BSPD. Don't worry if you don't know what the acronyms are. Also, people who just walked in, if you want to follow along on the SN4 diagram, I sent it out in the education channel. If that helps you learn, if you just want to look at it up here, that's also good. So previously the APPS, which stands for accelerator pedal position sensor, I'm trying to get people to call it the PCU now because powertrain control unit is what like industry calls it, and it actually explains what it does a bit better. So it takes in the two accelerator pedal encoders, and they have different voltage slopes for their angles. So basically what that looks like is their encoders, so they're doing a rotation. So it's a sensor that's rotating, and that gives you a different voltage output based on your position. And those have to have different slopes because we want to make sure that in the event if those signals got shorted together, or if you only had one and you only had one signal, that you wouldn't want to accidentally command a torque that wasn't what the sensor was actually at. So having two of them makes sure that if either of them is broken, then there's a discrepancy between where it thinks the two values should be, and so it won't command torque. And a similar idea goes for all critical sensors on the car. Most of them go from a 0-volt range to a 5-volt range. So there's some analog value between those, and that corresponds to whatever value it's sensing. And so the only valid values are from 0.5 volts to 4.5 volts. So we have half a volt of headroom and tailroom. And basically what that does is if the sensor signal was shorted to power or ground, that's an invalid value. So if you messed up harnessing or you plugged it in wrong, it wouldn't actually think the sensor's connected. It'd be like, hey, this is out of range. This is not okay. And so that is just an extra level of safety. And so additionally, this board takes in two brake pressure sensors. So in race cars, you have different pressure lines for your front brakes and your rear brakes. So there's two of them. And this is used for, well, number one, turning on the brake light. When the pressure gets high enough, the brake light on the rear will turn on by the PCU sending a message over the CAN bus to the LVPDB. And what what else do I have here? There's also a sensor slot for a brake encoder, but this isn't used because motorsport brakes basically just translate pressure from your foot to the brake lines. So they only move like 3 millimeters. Like it's literally just that much. And so it's not like there's no sensor that we're gonna buy reasonably that's that accurate. Um, and so that's sort of a legacy thing that we don't use. What else goes on here? So it converts those accelerator signals into a torque command. Right now, we just use a very simple, if the accelerator is not pressed, that's zero torque. If it's fully pressed, that's max torque, and it's a linear mapping of values. Um, More complex controls should be implemented this year, and hopefully if any of you are interested in doing like motor controls or like powertrain design, we should have a more complex algorithm. Namely, one thing you want to keep in mind is providing brownout protection, which is an issue right now. That basically means if I press the accelerator, I start pulling power out of the battery, right? And that's a current. And there's some resistance in your high voltage bus. So as you pull a current over that resistance, you'll have a voltage drop. And so if we pull too much current out of the battery, that voltage will go too low. And then the inverter it's seeing that lower voltage, right? And it's like, hey, there's no more power on the bus. This voltage is way too low. So it shuts off and it stops commanding torque to the motor. So you actually want a powertrain control unit that will start rolling back how much torque it's commanding if you start reaching that voltage drop limit. And like any of you who did the CAN bus project, CAN is very critical to the car. So torque commands are sent over the CAN bus from the PCU to the inverter. So does anybody have any questions on like powertrain control or yeah? Alex.
Powertrain control unit, it's the BSPD.
Yes, so the BSPD is a shield on top of it, and that's my next slide. Yeah. So let's talk about BSPD. So the brake system plausibility device, it's located as a PCB shield on the PCU. And the reason we do this is because it uses basically all the same signals, and all the sensors are located in the same area. So there's no point to route it to another location. It ensures driver safety, which is obviously number one priority, and it's required by the rules, but we want to keep our drivers safe. We want this car to be safe to operate. We don't want anybody getting hurt. So it causes shutdown if current is flowing out of the accumulator and the brakes are engaged. And the way it does this is by using the brake pressure sensors and HEX, which is it's just an acronym for Hall effect current sensor. If you guys are interested, you can Google the Hall effect. It's just a way to sense current through magnetic fields. And that's located in the high voltage box, which will be at the end of this presentation. And this goes into some analog logic. The BSPD, if you guys have seen that in the rules, it has to be analog. You can't have any digital control. And so this sits on top and it just gets the sensor signals directly, does its comparison, and either connects the shutdown circuit or doesn't. Does that answer? Yeah.
About the PCU, is that digital or is it also analog?
Yeah, so the PCU is a digital node which has a microbasic on it, and that's exactly because you're using CAN, you're going to need a digital node and a microbasic. But the sensor signals get routed directly to the BSPD shield before they go into the digital node. So the analog circuitry is doing all of its comparisons first, and then the digital node is like getting the information. Yeah. Okay, yeah, so that's a good question. PCB shields are like, it's just sort of a design way to put more functionality on top of PCB. So you have your main board, and then you're gonna put header pins on that, and then you're gonna design another PCB that has the opposite header pins, and that will plug in on top of the other one. So that's sort of like that's what microbasic does, where we have our main PCBs and then microbasic plugs into the top, and it makes it so that it helps you abstract away the actual implementation of that PCB and instead just have the inputs and outputs. Um, and so the reason we use it is because it helps basically two designers work on these boards who they'll communicate, but they're sort of working separately. And so their work doesn't rely on one another. So nobody's dependent on each other. Yeah.
Um,
Okay. Yeah.
Do you mind, what is the switchcraft? What is that?
Yeah. So switchcraft is just a name of a connector. That's the 4-pin connectors that we're currently using on the car. That's the manufacturer. So the reason you see that everywhere is because this diagram, we're also trying to use it as a harnessing diagram this year. So if you look at the color coding in the top left corner, it'll tell you what every color means for that wire. And then I listed out the connectors for every single one so that it's very obvious what type of connector you're plugging into. Oh, yes. So a harness diagram is basically it's basically like what the system diagram is meant to be. It's a huge sheet and it has every board, every connector, and then it has the wires that connect them. All the wires are called a harness or a wire harness. And so it describes what wires go from each node to all the other nodes and what pins on the connector that wire connects to. So it's basically a piece of documentation that allows you to manufacture the entire nervous system of the car. Yeah, yeah, it's basically just a giant schematic. Yeah. Except you don't have any, all the intelligent components are contained within PCBs. So it'll be like a schematic, but you're not putting components, you're putting like different boards. But yeah, that's a good way. All right. Um, Oops, I forgot to change the title on this one. That's meant to say dashboard. So now we're going to be talking about the dashboard, which is like what the driver looks like, what's in front of them while they're operating the vehicle. And so this is basically a panel on the front of the car. Um, I'm realizing I should have put more photos of the real car in this presentation so you guys can see what the dashboard looks like. But it basically has a display in the middle, some indicators off to the left, and some buttons and switches off to the right. And it contains shutdown indicator lights for the IMD, which is the isolation monitoring device. Abstract that away for a minute. We'll go over that in the shutdown circuit presentation. The BMS, which is the battery management system. So right, that's making sure all the batteries are being handled correctly. And so if that has a fault, the whole car shuts down. So there's an indicator light for that. And the BSPD, which is the brake system plausibility device that we just talked about. And it makes sure it basically has 3 indicators. So the driver can tell if one of those tripped and then which one tripped based on which light is on. This board also contains the inertia switch and the dashboard e-stop, which are 2 more shutdown circuit components. So if the driver hits the dashboard e-stop, it will disconnect the battery from the car. At a high level, that's what the shutdown circuit is doing. There's some relays in the battery, and relays are just mechanical switches. So they either connect the battery to the car or they latch open, and the battery is like physically disconnected from the car basically because these relays are open. And so that's what the shutdown circuit's doing at a high level. It'll either allow these to close or not allow them and they'll be open. And so the inertia switch is basically if you get into a crash, it's this it's like a metal ball inside of this plastic housing with a spring. And if it has too much acceleration in any direction, then it latches and it opens the switch. And then it has like a button on it. You can reset it. Yeah.
Sound like something you get like off.
Yeah, there's a specific one that the rule says you have to buy and put on your car. It's like the Sensata resettable crash sensor. Yeah. And then the dashboard e-stop also opens the shutdown circuit, but that's just like the driver hits it. So whenever the driver has to egress out of the car, that's the first thing they do is they have to hit the e-stop to turn off their car, take off the steering wheel, throw it out, undo their harness and jump out of the car. And every driver has to do that at competition in under 5 seconds, I think. in order to be like able to be a driver. Uh, no, the primary way that you should turn off high voltage on the car is with the tractive system master switch, which we'll get to in like 3 or 4 slides once we finish the LV section. But once you turn that off, it's also good typically to just press in all the e-stops just so it's like nobody can accidentally push one switch and then the whole thing turns on again. So it's extra factors of safety. Yeah.
Is this also where the
Where the what?
inputs get inserted?
Yeah, this also has the screen. So there's an additional dashboard PCB that's connected. And so something to specify that might have been unclear is the blue box is not an actual PCB. That's just like, that's the mechanical piece that everything gets mounted onto. So the indicator lights get mounted on there and they have wires running to the accumulator and the shutdown components get mounted on there and they have the shutdown wire running through them. And then there's an additional dashboard PCB that just connects on the side and that drives the display and reads the buttons on the dashboard, which has all your infotainment information. Although we call it infotainment just because that's like, it's funny and it's what the industry does, but it's like, there's not much entertainment going on. Although on the first car, we did play Rickrolls on the display because we had a Raspberry Pi, but Raspberry Pi added too much complexity, so that's no longer on there, sadly. Yeah. Yeah, so that's actually a really good question, and it's something that happened to us last year. So you can think of it, the shutdown circuit's like this big wire that goes all the way around the car, right? So it's a really long wire. So it actually has quite a bit of inductance, which we didn't realize. But with that wire going all the way around the car, when we would hit e-stops, it like immediately cuts it, right? And so if you have an inductor and you immediately cut the connection, then your voltage spikes up really high because inductors want current to keep flowing. So if it stops flowing, they drive up the voltage really high. And then it eventually comes back down. But those spikes actually got really high and were causing they were causing a number of things. Which we can go more in depth later. But yeah, there's some solutions that we were looking into. We're not really sure how to deal with it. It's an ongoing conversation. Mm-hmm. Yeah, that's very insightful. Yeah.
Are there any more wires in those three that connect to the dashboard?
Um, so this is definitely simplified a little bit because each of the indicator lights at the top has 2 wires because you have power and ground. So it's 6 wires at the top, and then the shutdown circuit that's just 1 wire going in, and then there's 1 wire that connects the two, and then 1 wire coming out. So you can think of it as 1 going in, 1 going out. So now we're up to 8. And then the display has 2 wires going to the dashboard PCB, and there's 4 buttons, and each button needs 2 wires, because you need to be able to tell if it's a short or if it's an open. So that's really, the buttons are like on the PCB is like behind the buttons, and there's connectors to like jump it. But yeah, that's like 8, 9, 10. There's like another 18 wires or like nets you have to think about. Yeah. All right. Amazing questions. I'm glad everybody's so engaged. All right. So LV system 4 out of 5. We're almost done with the LV system, guys. We're making good time. So if you have questions, like make sure to ask them. Don't feel like we're in a rush. Which speaking of, I'll also start trying to talk a little bit more slowly in case I was going too fast. All right. So now we're going to be talking about the sensor nodes and the data logger. So there's a front sensor node and a rear sensor node, and then our data logger PCB. And so the sensor nodes, in theory, are pretty simple. They basically take in analog sensor data and they send it onto the CAN bus. So it's basically just taking the sensor inputs And then you have to do whatever analog filtering you need, whatever sampling, and then package that into CAN packets and then send those out on the bus. Um, and so you can see the sensors that are connected to the front and the rear. Like we have wheel speed, linear potentiometers on the suspension to tell how far they're compressed. We have a steering wheel encoder to tell the angle of the steering wheel. We also have coolant temperature and flow rate. That's like a one integrated sensor that's in the back of the car on the coolant loop. Um, yeah, is there any questions on the sensor nodes? Yeah.
When you use the suspension layer potential.
Yeah, so it's actually for you it's actually so you can take the accelerometer data or like the IMU data, inertial measurement unit, and then overlay that with the four linear potentiometers. And you can tell when you're accelerating, like if we were doing a really hard turn, you'll use the IMU to tell how much acceleration you have into the center of the turn. And then you can look at how much your outer suspension is extending and how much your inner suspension is compressing. And then because you have four, you can also tell like if you're leaning down into the turn or if you have too much lift on the front of the car and you're like leaning back into the turn. And so you can basically overlay acceleration and the distance of each wheel from the chassis, right? Because the suspension is basically the distance from the wheel to the chassis. And you can do a lot of vehicle dynamics stuff. That's really cool. Yeah. Yeah, so a linear potentiometer is basically a resistor. You can think of it as like a long pole that has some resistance, and then it has another connection point on it that's a sweeper. And so that basically goes like up and down the pole. And depending on where it is on the pole, between the top of the pole and the sweeper, if it's really high, you'll have low resistance. And between the sweeper and the bottom of the pole, you'll have high resistance. And then if it's all the way at the bottom, you'll have low resistance between the bottom of the pole and the sweeper and high resistance. So basically, it's like two resistors in series and it'll change the size of each of them based on how far out it is. Yeah.
So there's a connection from the rear circuit to the PCU.
Yeah.
Is that for the PSPs to kind of once again check like plausibility or doesn't
Yeah, so the bus you're talking about is the green, black, and red wires, and then that gets bundled into the turquoise one. So that's our CAN and power bundle. So that's daisy chaining every node in the car together so they're all connected to the same CAN bus and get the low voltage power. Yeah.
like five other kind of buses?
Yes. So for those of you who didn't do the CAN bus project, CAN bus stands for Controller Area Network. It's a pretty big automotive standard, like all modern cars that are driving on the road use a CAN bus. And it's a two-wire protocol, and it helps you communicate information across the car. Getting a little bit more into the details, because you guys should all understand the hardware basics of how it works. It's a differential signal, which basically means you have two wires, CAN high and CAN low. Normally, they both sit in the middle. Once I finish micro basic updates, it'll be a 5-volt communication bus and not a 3.3-volt communication bus. So that midpoint is 2.5 volts. And then that's called a recessive bit, and that's a 1. Why a 1 is recessive? It has to do with like the ID arbitration. Like based on your ID, the higher your ID is, the more or the lower your ID is, the more dominant you are, right? And the lower your ID is, like you'll hit a 0 first, basically. And then, so that's a recessive bit. And then when a node on the bus wants to drive a dominant bit or a 0, it'll like force those two apart and it forces low down to like, I think it's like 0.6 volts or something. And it forces high up to I think it's like 4 volts or something. I forget the exact numbers, but it basically forces them apart. And so every node on the bus is watching this where it's like they're close together and then they're far apart and then they're close together and then they're far apart. And you can basically take that in and subtract the two signals, and then you get like 0, 1, 0, 1, 0, 1. Yeah.
Then how do you know which like PCB is using the CAN bus, like, or like so they're all using it? Like how does it know like what is doing it?
Yeah, exactly. So yeah, I'll go into it a little bit, but definitely look up like the message of the CAN bus structure, or honestly, come talk to me or talk to anybody who did the CAN bus project. It's also good for like you guys to explain things to each other, and then you're also educators, and we're all educators, and that's awesome. Um, but yeah, so the CAN bus initially like isn't used. It's sitting at 2.5 volts, both lines. Then let's say some node wants to start talking. It'll start by sending a startup frame. So it like pulls it apart. And so if two of them tried starting at the same time and they both pulled it apart, they don't realize the other one pulled it apart. So then let's say like some random number started transmitting and they both pulled it apart, then they let it go, and then they start sending their ID. And this is where the priority comes into play. So let's say like in 2 bits, ID is actually 11 bits, but let's say it was 2 bits. Let's say like you're very important. You have a lot of information. So you're priority 1, and I don't have a lot of information. So I'm priority 3. So I'm 1, 1, and you're 0, 1. So I would drive a 1. So I keep mine together, and you would drive a 0 as your first bit. So you drive it apart, and then I see, oh, I wanted it to be a 1, but somebody drove it apart. They're more important than me. And then I get off the bus and I just listen, and then you send your message. Um, and like if you send a 0, let's say 0, 0 was transmitting and 0, 1 was trying to transmit, then the next bit you drive a 1 and you're low, and then 0, 0 drives a 0, and you're like, oh, somebody more important on the bus is trying to talk. I'll like step off for a second. Yeah.
So for all different boards, the CAN system is just two wires that are being shared by all the different systems.
Exactly. And then an important note is at the end of those two wires, you have your termination resistors, which are 120 ohms across the CAN high and CAN low. And an important new thing that I'm adding onto MicroBasic right now is called split termination. So you can do the simple 120 ohms across. It usually works. For us, we were having some noise issues. So you do split termination, which is basically instead of 120 ohms, you do two 60 ohm resistors. And across the middle point, you do a capacitor to ground. And so now if you look from like the high or you look from the low, you see a resistor, then a capacitor to ground, which is a low pass filter, right? So it helps you filter out some more higher frequency harmonics. Yeah.
What's the difference between you mentioned you guys are going to like a 5 volt canvas system? What's the difference between like the 3 volt and 5 volt?
Yeah, it's basically just what the top of your communication is. So on 3.3 volt, it would be you sit around like 1.6 and then you drive apart to like zero point 0.8 and 2.9. And then on a 5 volt, you sit at 2.5 volts, then you drive apart. I mean, there's benefits and trade-offs for both. Like 3.3 volts, you have lower voltage, so you can save power if you have the same current draw. You also might be able to communicate more quickly, right? Because you don't have to move the voltage as far. Um, but 5 volts might be more robust if you had a lot of noise because you have more distance to move apart. So if there's noise, you're still above your threshold, but you spend a little bit more power. Yeah.
Which nodes have priority in your system?
Yeah, so I don't know the exact ID. We have a table you can look it up on, but like battery management system is like the top priority. Like I think it's 3 or something. And the only higher ones they're empty. They're just for like if something more important came along. But an interesting side note is that it's not actually the PCB that has an ID, it's a message type. So every message type is an ID. So like your BMS could be transmitting cell temperature, and that's like highest priority ID. for that message, but then it could also transmit another message ID of like, I'm counting from a 0 to 1,000 for fun. And it could do that as like priority FFF. Um, so like BMS is highest priority, then I think it's APPS because that's sending torque command messages. Um, and then I think it's LVPDB and then inverter. Inverter is an off-the-shelf component, so all its IDs were like pre-chosen. They're like they're all A and then something because it's also hexadecimal. So it's they're all A and then something. And then I think there's a couple other nodes, and I think we just put them way at the end because it's just not super high priority. Yeah.
So you mentioned that you guys were like getting some noise from campus,
Yeah.
but then like isn't this the part of like the pressure system with two wires on cam, like supposed to remove all the noise that you get?
Mhm.
Like what kind of noise would you guys get?
Yeah, so differential helps you get rid of common mode noise because so common mode noise happens in common to both signals. So if it's differential and you're subtracting, then that will get subtracted out, right? Because it happened to both of them. But our system only has finite range, right? So if you have too much common mode noise and you just go like you take both of them above the whole system's range, then that's going to break. So we had large common mode spikes, which were causing some issues. Um, and that's like the main one for what you're talking about. We also had some other types of noise, but we can get into that after. All right. Amazing questions, guys. I'm loving it. Uh, so that was the sensors, and then the data control unit. So we need to get all this information off the car, right? Like it's no good if it's stuck on some SD card. Um, so this logs all the messages sent over the CAN bus and saves them onto an SD card to be read later. It also has an XB, which you guys can look up the part number if you go and look at the schematic. XB is basically a wireless transmitter. And so you can have the other half of the XB and plug it into your computer, and you can actually wirelessly receive data from the car while it's like out on the track going around doing loops. It has like I don't know, it has like a mile range or something. Like you're not going to lose a connection. It's like a 2.4 gigahertz antenna. So it's like a Wi-Fi frequency. Um, and it's extremely critical for analyzing the performance of our car, right? Like us as the electrical team who's in charge of sensors, when mechanical people want data, they want feedback, right? Like every system needs closed feedback to improve. When they want data back, it's up to us to get them that information through this data pipeline. Because if they don't have that data to figure out what's happening with their current system, like how do you expect them to design a better system next year, right? So this is something that's really important for us to get right because like the rest of the team is counting on us for this one. So some examples of data we collect are like battery voltage and current over a race. So you can tell like how much power you're drawing, what your spikes look like, that whole, all that good stuff. Motor speed. Um, you want to know your actual motor speed as well as your wheel speed because if your motor's not spinning at the same speed as your wheels, that's something to start looking into. It might be something in your like you're slipping or something on your wheels, so your wheels spin faster. It might be something in the rear differential. So motor has a chain that drives a differential. I'm not completely qualified to explain how a differential works, but like your rear wheels can go different speeds when you're turning, is like as far as I know. So you want to tell the difference in those speeds. Also, your front wheels, we're rear wheel drive, right? So your front wheels aren't actually being powered. So if those ones start slipping and their speeds are way lower, then that's also something to look into. That I can go on about data forever. Like you guys know data is important. Information is everything in this day and age. Oh, that's another commanded versus measured motor torque. So I can send a command for 200 Newton meters to the motor, but if the motor's like, or the inverter and the motor can talk to each other and it can sense how much torque is actually at the output of the motor. We can also go into motor control forever. There's so many things to talk about. if your commanded and your measured aren't matching up, then something's physically limiting your motor that you should look into. And this is another important thing. On SN2, our commanded and our measured torques, SN2 was like the first time we got our data pipeline up and running. And we're like, wait a minute, our commanded and our measured torques aren't lining up. Why is, because SN2 is going really slowly. We're like, why is it going so slowly? We're like, oh, it's not actually doing what we're commanding it to do. And then we ended up looking even further into the inverter, and it turns out there was like one status variable that we just had to increase the limit on, which was if you're interested in motor control, it was the IQ limit current. So you can go look that up if you want. But that was basically limited too low. We increased that. The car like literally started going like 50% faster. So you can see how important data is because it's like you can change one variable on one thing, and it's like if you're not very diligent and careful about every variable, uh, some things can bite you in the butt like that. Also, coolant temperature is very important, right? Also, I've been saying a lot about the coolant loop. Quick note on that. You have like the coolant pump, which is causing this distilled water to go around in a loop, and it cools the motor, the inverter, and then it goes through the radiator, which allows air to go through it. So you have airflow going through that to cool the liquid back down once it heats up in the motor and the inverter. And then it also has like a fill valve and a empty valve to service it. All right. Lots of information. Any questions? Yeah. Yeah, so coaxial is the type of cable that's used. So coaxial is like you have like a solid rod down the middle, and then you have like a larger ring around it that's your shielding. So typically it's like signal down the middle and then like shielding around it. And so that shields the entire connection. And it's called coaxial because like the two cylinders have the same axis as they go down. And it's used for RF connections or high speed connections. So if you have like a high speed clock or an RF connection like this. And so that's basically taking the XB antenna. And because if you actually put the antenna on the PCB, then you put it in the box and then you like shoved it down inside the car, the chassis is all grounded low voltage, like the chassis stored low voltage. So you just took your antenna and shoved it into like it's not a great Faraday cage, but you shoved it into a Faraday cage that's like going to block some of the signal. So we have that cable so you can route it out of the box and then the antenna is actually on the top of the car. Yeah.
Inverter, a motor, what does the inverter do in that context exactly?
Yeah, we'll get to that at the end of the high voltage section, but very good question. Yeah. Yeah, it's the same data. And also this is so yes, it's the same data. Also something that's not going to be talked about in this presentation, but is an extremely good resource that our team developed is we have our team loves acronyms. We have DASH, which is not the dashboard. It's an online dashboard and it stands for Data Analysis and Storage Hub. And it's basically a website that we have that all of the car data is uploaded to, and anybody can go to that website, go to whatever log they want to look at, and then pick what signals they want to put onto the graph. And like, you guys should go talk to Rodwan about that because that was basically his recruitment project. And then he came on the team and like finished it. So yeah, if any of you did the web for this, the web one for the CS, that's like what you are probably working on. But yeah, did that answer? Okay, awesome. Now for the interesting stuff. That finishes low voltage. We're going into high voltage, dangerous territory. Does anybody have questions before we get into high voltage? Yeah.
Yeah, I'm just looking at the diagram. So for the data logger,
Uh-huh.
how does the front side of this window data get like transmitted there? So there's only connections to the rear sensor node.
Did I mess up the diagram? So the oh, you can't see my mouse. So around the middle, you're talking about the rear one at the bottom.
Yeah.
And then you have the turquoise cable, which is our CAN and power bundle. And so that goes to the PCU, and then that gets daisy chained to the front sensor node, and then that gets daisy chained onto the dash. And so that's the CAN bus is inside of yeah, it's turquoise so that we only have to route one wire instead of all three the entire distance. Yeah.
And then like for the PCU board,
Uh-huh.
is the whatever torque signals we're like giving to the rest of the motor and stuff, is that also through CAN or is that through different?
That's also over the CAN bus, yeah. And torque signals go to the inverter. The inverter takes care of all of that.
So they're using the same two wires, like that go all the way through all the
Yeah. Yeah. CAN can have up to like, I don't know, depends on what data sheet you read. Sometimes they'll quote like 500 nodes. It's like, I don't know who's putting 500 nodes on their CAN bus, but it's like, yeah, it's like super robust and it's only getting like higher and higher speed. Like it can go up to gigabit now, or megabit, sorry. It can go up to megabit now, and it's starting to get to like tens of megabits. Although we only run at 500 kilobits because we don't have that much stuff to talk about on the bus. Yeah. Yeah.
We talked about CAN, like, you said that's a, being like really robust. Is
Mhm.
there ever a situation that arises where the CAN bus gets overloaded with too many like you can count the 500 nodes for like two data points, stuff like that on one bus?
Yeah, there's definitely a point of bus saturation where you're not transmitting fast enough and too many things want to talk. And there's also the worry of like if an important node keeps hogging up the bus, the less important ones are going to stay quiet and not transmit their information. So you don't want like if BMS is over reporting its data, we don't want to like not get any information about wheel speed because BMS is hogging the bus. So there's another level of arbitration for that on the software side where it's like if you're waiting too long to send your stuff, like you just jump in front of the line. Um, but what we do to make sure that you're not saturating too much is you just there's like ways to be like, okay, these nodes are sending this often for these messages, and then you just see make sure we're not sending too many messages for the speed of the bus. And some cars add like a second CAN bus for like important information versus less important information. That's what we used to have, but we never got enough nodes to use the second CAN bus, so we're downsizing to reduce harnessing complexity this year. Um, but yeah, you that's called bus saturation, and it's something you need to calculate. All right. Uh, high voltage. So we started the low voltage section with turning on the grounded low voltage master switch. And now we're turning on the tractive system master switch. So both of these are on that right panel of the car. Low voltage is surrounded by a red circle. High voltage is always orange, just so everybody's aware. This one's surrounded by an orange circle. Um, and so this has a yellow wire going through it, which is shutdown. So this is what you should turn on last in the shutdown circuit to complete it and start pre-charging the car. If you did the pre-charge project, you know what I'm talking about. If you didn't do the pre-charge project, we'll explain that later. But yeah, so track the system master switch. It turns on the high voltage systems, i.e., it's connecting the accumulator to the rest of the car. So it's the last thing you should turn on in the shutdown circuit, and it's actually making those contactors close and connect the battery to the car. And it only does so if the rest of the shutdown circuit is closed, because if any node on the shutdown circuit is open, it won't connect those two. And once it does so, the ready to move indicator will start flashing amber. There's some special notes here. So this year, the rules are changing. Previously, there was a tractive system active light, the T-cell, and that was a light on the top of the car that was solid green when low voltage was on and flashing red when high voltage was active. basically the tractive system was higher than 60 volts. This year they're changing it. Now they have a ready to move light, which is on the top of the car. It will not be on. And then when there's more than 60 volts on the tractive system, it will start flashing amber. And I think I talk about it later, but there will also be tractive system status indicator lights, which is another light on top of the car that is solid green when you don't have BMS or IMD faults, and will be flashing red if either of those have a fault. So previously, solid green if it's okay to approach the car, flashing red if high voltage is on. Now, it's okay to approach the car if it's solid green. If it's flashing red, that means the battery management system or the isolation has tripped, that it's not safe to approach the car, it's not safe to touch the car. Until you guys learn more about the system, like come find an ESO, which I also don't think we've explained what ESOs are, but ESOs are electrical safety officers. It's a competition required role. I don't know who the current list is, but I'm on that list, so you can find me, or it's mostly like senior members like me, Smith, Amal, Nikhil, Michael, like people have worked with high voltage a lot. And so if it's flashing amber, also don't approach the car. That means high voltage is active. So now there's sort of like 3 states to not approach. Any questions? All right. We are running low on time, so I might go a little bit faster, although high voltage is very important. So please stop me and ask questions because this is super important to understand what's going on, especially because you're the people that people are going to turn to if they're like, oh no, the car's not working, it's an electrical issue. They're going to look to the closest EE or CS member because you guys are like the ones who are meant to understand, hey, the car's not working, it's not safe to approach. We need you to figure it out. So the first part is the BBB. This is the big battery board. Nikhil loves his acronyms. Most of the acronyms on the car are his. So this is Nikhil's. It's if you have to look it up in Altium though, for some reason it's not called BBB in Altium. It's called single board integration. And it's basically the battery control board. It's called big battery board because it integrates what used to be a bunch of smaller boards on SN1. And so it has 2 main functions that we'll talk about here. The first one is the battery management system. It serves as the BMS motherboard. And so it talks to all of the battery management system aux boards. So there's 1 aux board on each segment. You might have seen those during tabling. We like to take them out because they're the biggest board we have. And then 2 daughter boards plug into that. The daughter boards are what actually have the intelligent circuitry on it. And then those daughter boards are daisy chained and go up to the motherboard. BMS architecture is it's like a little bit complicated if it's your first time looking at a circuit. So we will go more in depth into that at the end of the semester. We're going to have like each system like deep dives into them. So ask any questions, but I understand it might be a little bit unclear, especially because I don't have great graphics up here. And so that senses voltage and temperature. And this will shut down the car if the temperatures or voltages are out of the safe operating envelope. And it also causes shutdown if current out of the accumulator is at an unsafe level. And it also helps facilitate charging the batteries and balancing the cells. So if you did the BMS state project or the BMS hardware project for recruitment, yeah, this is basically what you did. It has way more than 2 functions, like it says up here. This is just the first 2. All right, I'll go through the second half and then I'll ask for questions. The second half is the IMD driver. So let's talk about isolation for a second. The IMD is required by the rules. It's another one where it's like they give us a specific part number. You have to buy this. You have to put it on your car in this way. And they check that at inspection. And basically what it does is it senses if there's a short circuit between high voltage and low voltage. That doesn't emit. Okay, this is a leftover from previously slide. That does not mean that it will result in death and the battery exploding. That's not exactly what isolation does, but it is a safety thing. So you have separate low voltage and high voltage positive and negative poles for isolation. The reason that we have that is because the chassis of the car is low voltage ground, and then we have our low voltage power routed around the car, right? On high voltage, we have inside of the battery, we call it high voltage minus and high voltage plus. Once it goes across the errors, sorry, they're just called IRs now. Previously, it was accumulator isolation relays. This year in the rules, they changed it to just isolation relays. Why that was a necessary change, I don't know. So inside the battery, we call it HV plus and HV minus. Once it goes through the IRs, we call it tractive system plus and tractive system minus once it's outside the battery. They're the same thing, like they get shorted together. It's just a distinction so we know if we're talking about inside of the battery or outside the battery. Because if you're before the isolation relays, that's always live. Like as soon as you plug that in, it's just copper, like it's gonna conduct. But then once you're across those relays, it might not be live. So that's like the tractive system. And so the reason these are separated is because let's say we just shared a common ground. Let's say our high voltage battery was the same ground as our low voltage battery. So I'm doing my thing on the car. I'm like leaning over the car. So my body's touching the chassis, right? And one wire broke or somebody did something wrong and I accidentally touched something and that thing had gotten shorted to high voltage positive. There's now a short circuit, like a closed loop between the battery and myself, and current starts running through me. And that's not good. You don't want current running through you. So the IMD creates what's called a two-fault system. So if I'm working, leaning on the car, I'm now touching low voltage ground. And let's say something got messed up, the battery, like somebody did a wire harness wrong, and it got shorted. I lean over, and I touch high voltage plus. That's not a short circuit because there's no current loop that you can draw because nothing else is shorted to the high voltage minus terminal. Because my one half of my body is touching low voltage ground and the other half is touching high voltage positive. That's not a complete loop. So there's other it's still not good to touch high voltage. There's other things that might happen to you. Like they might not be at exactly the same level, so you might get a nasty shock because they're rebalancing to be the same level. But like it won't be severe injury. It just might give you a nasty shock. That will definitely hurt and might burn you, but you won't die. The isolation monitoring is making sure that if high voltage minus gets shorted to grounded low voltage or high voltage plus gets shorted to grounded low voltage, the car will like shut down, it will not turn on, and it'll like start flashing the red light now, right? Now the red light means IMD or BMS has a fault. And so you should not approach the car unless you have high voltage gloves and you're high voltage trained and you have some idea of what the system might be doing. But hopefully you guys will have that understanding by like the end of the semester, the end of the year. So yeah, this is a very important one that like needs to be done right because it has a lot of safety related with it. As most things you'll realize on the battery team, there's a lot of safety stuff. Like other students are working on this car, like you have people's safety in your hands. You got to make sure you do things diligently and do them right. So is there any questions on the like control board inside the accumulator? Our next stop is talking about the actual accumulator itself. So is there any questions about this? Yeah. Yeah, so that's for you need a light embedded in the accumulator lid that is normally off and will turn on if there's ever more than 60 volts outside the accumulator. It's called the high voltage indicator. So you might be thinking, oh, isn't that like what the ready to move light is supposed to do? This one has to work when the battery is in the car and also when the battery is just sitting by itself on a table. So if somehow something really bad happened and the battery's just like sitting somewhere and somehow the isolation relay is closed, it'll go red and you're like, whoa, I should not touch that battery. But it also means like you have to take the battery out of the car to charge it. Like we don't charge it while it's in the car, we charge it when it's external. So it also tells you like, oh, there's high voltage outside the battery because it's charging. Yeah. Yeah, so the IMD is the actual thing that the competition gives us, that you have to purchase. It's like a Bender isolation monitor. And then the IMD driver, that arrow at the bottom just goes to the connector that then goes to the dashboard. So it's basically just a set reset latch so that when the IMD senses an error, it sets that latch, and then there's a reset button on the car to reset it. So it's basically just a latch for a light. Yeah.
High voltage and then blinks the light or something.
Yeah, so the high voltage indicator is a red LED embedded in the casing of the accumulator, and it'll just turn on solid when there's high voltage outside. And then the you're talking about the high voltage indicator versus the IMD light.
No, the voltage driver right next to the IMD.
Oh yeah, it does the same thing except it's it's not a latch because it's only when the condition is persisting. So it's not a latched condition, it's just a like if true condition. And that's driven by the 600 volt DC-DC converter, which I meant to update this photo. It's not a 600 volt DC-DC anymore. It's something called a flyback converter. If you're interested, that was like Smith's project freshman year or sophomore year. If you want to talk to him about that, Shamila's working on it now. If you want to talk to her about it, yeah. Alex.
Well, talking about like souls to the low voltage and they touch the high voltage plus.
Mm-hmm.
It's like they're not, it's like low voltage and like, and then they touch the high voltage plus. I was a little confused on that part.
Yeah, so it's the differences between having a system where your high voltage battery and low voltage battery share the same ground. So like think of the battery as a voltage source. And if the negative terminal of both of those voltage sources was shorted to the car, like they're connected, right? And so if I am touching the car with one hand and I touch the positive side of the accumulator with my other hand, I'm basically touching HV minus and HV plus, and now I've created a closed circuit. However, if HV minus was not connected to grounded low voltage, because the way we're touching low voltage, right, is like we're touching the chassis or something related to the chassis, and then I touch high voltage plus, there's no like current loop that you could draw. All right, so now talking about the more, like this whole box here is the accumulator. So more now talking more generally, miscellaneous accumulator stuff. Accumulator isolation relays. They're just called isolation relays now. They're switches that physically open to shut down the car. And so those are shown at the top and the bottom. They're like, it's like a piece of metal inside, and then there's like an inductor below it. And so it's like I don't know, relays are pretty cool. It's like an inductor. So when you run current through it, there's like a magnetic force that will like force the switch closed. And then it's like normally open. So when there's not a current going through that, creating a magnetic field in the coil, then it like goes back up. Um, or it might be tough. I don't think it's gravity dependent. So I don't actually know what causes it to go back to resting position, but that's how it works. And so that's what the shutdown circuit is. It's the power for that isolation relay. And so if that power gets cut anywhere, like power can't get to the isolation relay to turn it on. And then there's segments. Yeah, Evan used these are slides I didn't update from Evan yet. You can think of it as 7 AAA batteries that we have to connect to the car to. They are much more dangerous than 7 AAA batteries, so don't treat them as AAA batteries. And then there's interlocks. Interlocks are a very important thing. They're also in the shutdown circuit. They're these big orange connectors that have two big poles on them, and that's what you use for high voltage plus and high voltage minus. And then like but when you look at one of the connectors, in between the two, you'll see two smaller wires. And inside of the connector, those two are actually shorted. So when you put the connector on, the shutdown circuit is going through that. So if it's on correctly, it'll allow the shutdown circuit power to go through that. But if it's not on right and it's not like shorting the pins, then it can't go through. Or if the connector is not present, then the contactors can't close. And so that you need interlocks on every high voltage connector. What else? I think that's there's also the IVT, which is a current sensor, but that's also undergoing some design changes. So if you're interested, like talk to Rick, or I think Nathan's working on that. But yeah, any questions on the battery? Yeah.
What's the main use one?
Yeah, that's you need like physical protection. So that's basically a physical device that if more than 60 amps was going through it for too long, it would burn and disconnect the battery. So if the digital protection doesn't stop it first, you always have like a real physical solution that will break your battery if too much current was exiting. Yeah.
I didn't see it on that diagram, but there's a front and rear dart,
Oh yeah. I forgot to update this photo. Dart is I don't know. It's another one of Nikhil's acronyms. It's
um,
D D stands for like dynamic, I think, but it's air it's like dynamic air routing something. It's a fan controller.
oh,
It basically is a PWM controller to make the accumulator fans blow faster or slower. And they're connected to the CAN bus, and then they're not in the main attic of the accumulator, they sit like on the ends where the fans are. And it's basically an attempt to reduce harnessing to the fans. So instead of having to like connect a PWM and a sense wire from every fan back to the attic, you can just connect CAN and power to this small PCB right next to the fan to reduce harnessing. Yeah. Yeah, the acronym's in Notion, I think. I forgot what it stands for. It's a fan. All right. Yeah.
my DMS project was, on at least on a 12S14 battery.
Yeah.
Is there a human data that, layout, or is it different than that?
I mean, series and parallel counts apply to all battery systems. So, yeah, like our battery last year was 140S 4P, and I think this year, because we're trying to do custom cells, I think they're doing like 115S 5P or something. And that's like something the Sims team has been working on, trying to do different endurance tracks and figure out like how much energy we need, how much current discharge we need, what like the voltage throughout the race would look like. Yeah. All right. High voltage box. So this is a very important thing that has gone slightly neglected for the past 2 years, although last year Weston and I teamed up to try to knock it out, and Khalid worked on it. But this definitely needs more attention this year to clean it up. And I think somebody on Accumulator is doing like a PCB to try to simplify things inside of it. But it basically, oh, I didn't make a second slide for this one. It has a lot of things in it. I would go through this diagram and read it. Some important notes. It has the HVD, which is slightly different than an interlock. It's externally facing, and it's this like rotating dial, and only one pole of the accumulator goes through it. So high voltage plus goes through it, but not high voltage minus. And it's a rotate to remove thing that has to be accessible from the back of the car. So basically, if something's happening, you can run up to the car, rotate it, and it will physically disconnect the battery from the car. So basically, like if your isolation relays weren't opening for some reason, you can still like disconnect the battery. It also has the discharge circuit inside of it. So when the isolation relays open and the battery is disconnected, the inverter actually has a big capacitor at the front. And so the tractive system is still high voltage. And so the discharge resistor, when it loses shutdown power, will short tractive system plus and tractive system minus over a resistor to basically short the capacitor to a resistor and discharge it. And it has to bring that under 60 volts in like under 4 seconds or something, I think. 5 seconds. Okay. Um, it also contains the Hall effect current sensor we talked about earlier for the BSPD. It also is where there's a competition required device called the energy meter, which is another inline device that you have to screw in series with your negative terminal. And then it has a connector to go to your positive terminal. And it's a competition device that logs your tractive system voltage and current. And they, after every event you do at competition, you have to take your car back to their tent and they'll download their data. And they track data on how much power you're using during every event because there's an efficiency score. Although the efficiency score is only for the endurance event, but they still collect your data for like acceleration and skid pad and autocross. This is also the connection point for the tractive system measurement points, which I think I have a later slide about. So I'm gonna go on to the next one. We're almost to the end there. Hang in for like 10 more minutes. Does anybody have questions on this? All right. Now we're gonna talk about e-powertrain, which has never been an official sub team, but has always been like a dedicated 1 or 2 people on LVEE have been the like pseudo e-powertrain sub team. And they usually manage themselves, but it's basically a term we use to describe the inverter and the motor because the powertrain sub team sort of deals with like they mount the inverter and the motor and then they put the sprocket onto the motor, but they don't really think about like how is the battery energy getting to the inverter, how is the inverter driving the motor, things like that. So first half of e-powertrain, the inverter, aka the motor controller. So like you were asking about earlier, it controls the motor. It receives torque commands from over the CAN bus sent by the powertrain control unit. And it converts the DC power at the input from the accumulator into 3-phase AC power. So it's 3 sine waves 120 degrees apart from each other. And it uses that to control the torque and speed of the motor. It performs mathematical operations to figure out how to do that control. There's a lot of control theory that goes into that to control that, some transforms. But it's cool stuff if you're interested. I'm happy to talk about it. I'm doing R&D for a custom inverter right now. So this is what I am thinking about. It also, an important thing, it shuts down if the motor's too hot. And this is sort of like an independent shutdown that like nothing else in the car is really thinking about. Like it'll monitor motor temperature and motor state, and it'll like shut down if something's wrong with the motor. And when I say shut down, that doesn't mean the shutdown circuit. That means like it will just stop commanding torque. It'll stop sending signals to power the motor. And so the motor will stop spinning. And the inverter will throw a fault onto the CAN bus and be like, hey, like this is the reason you shouldn't operate right now. Does anybody have any questions on the inverter? All right. Motor. It's the whole car, right? Like this why did we take this long to get to it, right? Like this is the only thing that matters. Yeah, so this is what actually applies torque to the wheels, right? Like this, if you think about it, you could get rid of everything else and you could just like apply power to a motor and like hop on top of it and roll away, right? But it uses 3-phase power from the inverter to spin, and it has a resolver attached to it that measures its speed. And a resolver is basically a type of magnetic sensor similar to an encoder. but it tells you speed. Although the inverter is integrating this speed and also telling you the like angle of the motor as it spins. And this allows for the feedback loop between the inverter driving the motor and then the motor telling the inverter where it is and how fast it's going. And motor temperature is also sent back to the inverter. There's a lot of stuff that goes into motor design. There's currently a powertrain project that's doing R&D to see what would need to go into developing our own motor and manufacturing that. It's a very complicated electromechanical integration issue, but motors are super cool and it takes a lot of overhead to start manufacturing them, but that would be something that's really cool. And yeah, it's located in the back of the car. Does anybody have questions on the motor? Yeah. We use an MRAX 228 high voltage motor, and we got that 3 years ago on eBay. Yeah. And it's probably not the best motor we could have chosen, but we purchased it on eBay before we started developing a car because we're like, yo, this deal's crazy. We got to get this one. Which probably was the right decision at that point in time. But we're definitely looking to, that's why we're looking into motor R&D. This one like is a little bit too high voltage for the like FSAE rule set. MRAX, EMRAX 228.
You guys kind of recycle the same motors across different car iterations?
Oh yeah, the team only has one motor. Yeah, so it's been the same motor on every car. It's also been the same inverter on every car.
It's one motor, not one for each wheel?
Yeah, so we have one motor, and then that has a chain sprocket on it, and that's driving another chain sprocket that has the differential in the back. And then you have two rods, I think they're called tie rods, going from the differential to both of the wheels in the back. Yeah. No. Motors cost too much to have a backup motor. Yeah, if your motor broke, you're kinda cooked. Like the inverter has almost broken multiple times, and we don't have a backup inverter, so we've been like kind of cooked like 3 different times and been like really freaked out by that. But like the inverter costs like $7,000, so it's like yeah, and like buying another motor would be like $10,000 or something. So it's like it's not a yeah, don't break it. That's why we have one and we just take it off the old car, put it on the new car. Yeah.
Just like other EV cars, like, I mean, not this one you guys have, like, motors, so.
So most FSAE cars actually use electric airplane motors. So MRAX is a manufacturer for like electric aircrafts. And that's just because they have like the phase cables coming off of one side and the spinny side coming off the other side. So it's like nice packaging, right? Because when you do an airplane, you want the spinny side out here and the wires going into the chassis. Which like there's not a lot of off the shelf, I'm going to buy an electric motor for an electric vehicle. Like most companies are developing their own. Like Tesla, Rivian, Lucid, like they all have custom motor drivetrains. So it's not like a lot of money is going into developing an industry for independent companies to only sell motors. Yeah, but MRAX and I forget what the other manufacturer's called. It's like Amtech maybe. Like basically only those two like support the entire FSAE competition. Yeah.
I don't know.
What is it? MRAX 228? High voltage or medium voltage? That's what we want. Let's get it. 5 grand. All right. You tell B&O and then I'll watch as they like attack you.
I can send it to you. I don't know.
Oh, eBay as well? Oh, let's go. Deals on eBay. Okay, honorable mentions. Um, Other indicators. I sort of talked about this while we were doing other stuff. Tractive system status indicator. Like I said, the rules changed this year. Solid green when there's no faults. It's on top of the car. Flashing red when there's a BMS or IMD fault. So don't approach the car when it's flashing red. Once you guys understand more about the car, like approach with caution if you're the person who's like been assigned to try to figure out what's going on and like de-escalate the situation. And always wear high voltage gloves if you're going to approach the car in an unsafe state. Um, and we'll go over proper PPE on Thursday at GM. And then the ready to move light, it flashes amber when the tractive system is greater than 60 volts. So also don't approach the car when it's flashing amber, unless the driver like has egressed and needs help, or the driver stopped moving and is like needs help. And once again, only approach with proper PPE, which also includes one or two people behind you running with you carrying fire extinguishers. So yeah, like don't approach by yourself, and then make sure you have proper PPE. And we'll go over all that on Thursday. And then this, so those are on the roll hoop. And then on the master switch panel, which is that thing on the right side of the car that we've been talking about, you have like grounded low voltage master switch, tractive system master switch. You also have the tractive system measurement points, which are these banana jack plugs. So basically anybody can walk up to the car with a multimeter and like plug in their banana jacks, and you can like monitor the tractive system voltage. You also need them because they'll test your isolation monitoring. So they'll go up to the car and they'll plug into high voltage plus and plug the other side into grounded low voltage, and they'll short them together, and they'll like make sure you latch in time, and then high voltage turns off. And then they'll plug into low voltage, plug into HV minus, short them together, make sure you latch and shut down in time. There's also the reset buttons. So like the three latching shutdown, the three digital latching shutdown nodes are BSPD, BMS, IMD. So that basically, there's three reset buttons for each of those. And those can't be driver accessible. So they're like back on the master switch panel because you're like strapped in. So you can't like go back and touch it. So it's only accessible by somebody walking up to their car. All right, last slide. I didn't want to put this in the low voltage one in case we didn't get time, and we're already over time. So quickly, debug port, easy access under the hood. If you guys see, this is like in the diagram, it's all the way at the end past the front sensor node. It's just under the hood. It has a DB9 port, which is a type of connector for the off-the-shelf data logger to connect to. That's our backup data logger in case data logger doesn't work this year, and it's what we used last year. It's just like a little brick that just senses your CAN bus and logs everything. And it also has a 4-pin switchcraft for power as a debug port. So this is a very good spot for if you need to figure out what's going on with the car, go with your laptop, walk up. I think we're going to try to get Savvy CAN up and running for everybody. So your laptop will basically be able to read CAN. So you can go up, plug in, and see what's going on with the car. So yeah. Oh, and there's my time. All right, that's everything. Does anybody have any questions before we wrap up and I end the recording? Yeah, Alex.
The question about like in general, I guess that had any problems like with pulling like low voltage PCBs and stuff like that, or not?
No, the low voltage PCBs haven't don't burn that much power. For reference, every single low voltage PCB across the entire car summed together is half an amp at 24 volts. So yeah. Yeah.
Once like that,
Uh-huh.
there was a right e-stop and a left e-stop. Why the right one and the left one?
So like somebody coming from the left side of the car or somebody coming from the right side of the car can run up and hit the emergency stop. Yeah. Yeah, that's also part of the shutdown circuit. Yeah. All right, I'm gonna stop recording.